Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll explore GPU offloading with OpenMP using the A-100 nodes on the Saga Linux cluster. Previously, we used OpenACC for GPU offloading on these nodes. In our previous video, we created a new directory called OpenMP on A-100 in the work folder on Saga. We'll now use this directory to submit job scripts and explore GPU offloading with OpenMP. In our last video, we copied a Fortran program that utilizes GPU offloading with OpenMP into our new directory within the work folder. Let's begin by exploring this Fortran program that implements OpenMP for GPU offloading. We will use a matrix of size n equal to 16384. The same dimension we used in our previous multi-core parallel computing with OpenMP. I have created 4 versions of this program, with file names ending with 1 through 4. The first program, with file ending 1, utilizes a nested loop structured in the natural order of I, J, and K. The next program, identified by the file extension 2, uses the same loop structure as the Intel Fortran compiler with the loop order J, K, and I. The program with file ending 3, apply the K loop as the innermost loop, and thus using the loop ordering J, I, and K. We apply the same loop ordering of J, I, and K in the program with file ending 4, but we collapse the 2 outermost loops. Note that all these programs use the target directive for GPU offloading. This directive specifies that the code block between target and end target should be offloaded to the GPU. To transfer matrix data to the GPU or the device, the programs use the enter data directive combined with the map to option, which offloads all matrices. When transferring data back to the CPU or the host, we use the map from option. This specifically moves only the C matrix data back, as it is the only matrix that changes during the matrix multiplication loop. For parallel multi-core computing, we use the parallel do directive. Previously, we've utilized up to 32 threads on Fram and up to 128 threads on Betsy. The A-100 GPU has 6,912 cores, allowing for the same number of threads to perform matrix multiplication. However, achieving good efficiency with more than 16 or 32 threads is challenging. Therefore, when offloading to a large number of GPU cores, organizing the threads into teams is essential. This setup limits the number of threads that share memory or data to those within the same team. The Teams directive organizes the threads into teams, and the Distribute directive distributes the iterations of the matrix multiplication loop among the teams. In our last video, we copied the testing GPU script into our new directory within the work folder. In the testing GPU script, we will use the A100 GPUs, since the P100 do not support OpenMP offloading. The offloading will be set to OpenMP. We will start with the first Fortran program with file ending 1. To monitor the GPU usage, we set monitor variable equal to on. We must remember to set the matrix dimension equal to 16,384. Additionally, we will execute the program just once, so we won't calculate the average wall time. We have set the CPU billing rate to 8. The performance will be calculated as before, using the compilation optimizations for the A-100 GPUs. The compilation option for OpenMP offloading is used. The testing GPU Python script outputs the performance data in the end of the testing process. In our last video, we copied a job script into our new directory within the work folder. We will execute the testing process as a batch job using this job script. The partition option guarantees that the job will be executed on one of the A100 nodes. The job script requests one CPU core and one GPU. We will be placed in the development queue and use recommended settings for error handling. We need to load the latest NV Fortran compiler and switch to an environment that supports the AMD architecture. Once these specifications are set, the job script can run the testing GPU Python script. We will first conduct a performance test using the Fortran program identified by file ending 1. The Fortran program, with file ending 1, uses a nested loop structured in the order of I, J, and K. Let us move to the directory that we made in our previous video. This directory is called OpenMP on A100 and is located in the work folder on Saga, and it contains all the programs and scripts that we are using. We can now use the sbatch command to submit this job to the Slurm workload manager, and we see that the job has been assigned the number 11, 62, 94, 60. Using the sq command, short for show queue, we can see that our job is currently pending as it waits for resources. After some time, we use the sq command again and observe that the job has completed. We can use the ll command to check if the job has produced the Slurm output file with the job number 11629460. We see that the Slurm output file has been generated, and we can view it using the Emacs editor. In the Slurm output file, we see that the test was conducted on the GPU 12.7 node. The file also contains some warnings and notes, which we can remove to enhance clarity. The first output is generated by the command that switches to an environment supporting the AMD architecture. The testing Python script outputs the compilation command, and we observe that the minfo option does not produce any compiler optimization notes during OpenMP offloading. The wall time for this Fortran program is approximately 51 seconds, achieving a performance of about 22 gigaflops. The testing Python script creates a monitor file, which we can review. This file indicates that the GPU utilization was 100% and the memory utilization was 50%. We will now conduct a performance test using the Fortran program identified by the file ending 2. The Fortran program with file ending 2 uses the same loop structure as the Intel Fortran compiler, with the loop order being J, K, and I. We can now submit this job to the Slurm workload manager with the sbatch command. The submitted batch job is assigned the job number 11, 62, 95, 28. We can open the Slurm output file with the Emacs editor to view the performance test results. The Slurm output file shows that the test was run on the GPU 12.5 node. To improve clarity, we can remove the warnings and notes from the file. The first output is produced by the command that switches to an AMD architecture-supported environment. The testing Python script displays the compilation command. The wall time for this Fortran program is around 584 seconds, with a performance of about 2 gigaflops. This is surprisingly poor, given that the loop ordering recommended by the Intel Fortran compiler performed best when using OpenACC for GPU offloading. This clearly indicates that OpenMP and OpenACC behaves differently for GPU offloading. The testing Python script generates a monitor file that we can review. This file shows that GPU utilization was 100%, while memory utilization was only 10%. The low memory utilization suggests that this Fortran program did not have the optimal loop ordering for OpenMP offloading. We will now conduct a performance test using the Fortran program identified by the file ending 3. The Fortran program with file ending 3 uses the K loop as the innermost loop, with the loop order being J, I, and K. We can submit this job to the Slurm workload manager using the sbatch command. The job is assigned the number 11, 62, 96, 63. To view the performance test results, we can open the Slurm output file with the Emacs editor. The Slurm output file shows that the test was executed on the GPU 12.3 node. To improve clarity, we can remove the warnings and notes from the file. The testing Python script displays the compilation command. The wall time for this Fortran program is around 62 seconds, with a performance of about 18 gigaflops. This is lower than the performance of the first test, with the natural loop ordering of I, J, and K. Consequently, we will test another method of OpenMP offloading. The testing Python script generates a monitor file that we can review. This file shows that GPU utilization was 100% and memory utilization was 42%. The memory utilization is slightly lower than the first test, which had 50% utilization. We conclude this video with a performance test using the Fortran program identified by the file ending 4. The Fortran program with file ending 4 uses the K loop as the innermost loop, with the loop order being J, I, and K, but we collapse the two outermost loops. We can submit this job to the Slurm workload manager using the sbatch command. The job is assigned the number 11, 62, 97, 12. To view the performance test results, we can open the Slurm output file with the Emacs editor. In the Slurm output file, we see that the test was conducted on the GPU 12.7 node. The file also contains some warnings and notes, which we can remove to enhance clarity. The testing Python script displays the compilation command. The wall time for this Fortran program is around 22 seconds, achieving a performance of about 50 gigaflops. The testing Python script generates a monitor file that we can review. This file shows that GPU utilization was a 100% and memory utilization was 100%. We can summarize our findings in a table format, showcasing the impact of different loop orders on performance and wall time. Using the loop order IJK, we observed a wall time of about 51 seconds and a performance of approximately 22 gigaflops. The loop order JKI, which performed best with OpenACC offloading, resulted in a much longer wall time of about 583 seconds when using OpenMP offloading. Another configuration, JIK, recorded a wall time of about 62 seconds and a performance of around 18 gigaflops. Notably, the best performance with OpenMP offloading was achieved with the loop order JIK, where the two outer loops, J and I, were collapsed into a single loop, reducing the wall time to 22 seconds and boosting performance to about 50 gigaflops. These results demonstrate the significant effects of loop ordering on computational efficiency with OpenMP offloading. We will not conduct further testing of OpenMP offloading on a single GPU. In our next video, we will explore OpenMP offloading on multiple GPUs, applying OpenMP for multi-GPU parallel computing. I am looking forward to the next video, wishing you all happy computing in the meantime.